turn to page 514. And what we're going to do is we're going to look at the trig functions for sine, cos, and tan, and what their graphs look like. So what I'm going to get you to start with is on page 514, the textbook has drawn the graph of sine, but I don't like their scale, so I'm going to teach you the scale that we're going to like to use, which is our axis family, to draw our sine graph. So you can draw this on the side of page 514. Okay. So in your textbook, they've drawn it with pi over 3s and a bunch of pi over 4s, and it just isn't a great scale. We're going to use the axis family as our scale, and we're going to highlight a few things here that are important. Okay? First of all, the definition of a periodic function is a function that repeats itself, and since going around the circle repeats itself every time, sine and cosine and tangent are all periodic functions. And we call the length of time that it takes to repeat itself the period. So the first thing that we notice, and I would actually probably start from 0 because that's what our circle does. We think about our unit circle, we think about starting at 0. You go through all of these values and get to 360 degrees or 2 pi radians, and then the second time around the circle, it would all repeat itself again. So we have one period being 2 pi. Now you can see this period, and it's not bad actually. If I draw a purple dot where the textbook looked at it, to a purple dot there. Going from one minimum to another minimum completes one cycle. Here, if I started in the middle going up, right, I'm in the middle going up, how long before I'm in the middle going up again? So I go here at pi, I'm at the middle, but I'm going down in my graph. It's not until I get to 2 pi that I start repeating this cycle again and again. So I could take this part of the graph and just clone it and paste it over and over again, and that's what my whole graph will look like. So sometimes when finding a period from a graph, you can use minimum to minimum or maximum to maximum. Sometimes you'll just have a maximum and a minimum. And if you go from maximum to minimum, does that make sense that that would be half of a period? And then you could just double that to find the whole period. Okay? So we can say, and we have this in our notes, that domain is everything. We are going to make some special notes off to the side about the zeros. Because if you think about sine, which is your y-coordinate, and you think about where on your unit circle your y-coordinate is equal to 0, it would happen at 0, then at pi, then at 2 pi, then 3 pi, and it would keep going. But I could also go in the negative direction and get negative pi, negative 3 pi, and keep going in that direction. So what mathematicians need to say is, how do we write all of these down if there's an infinite amount of them? And we'll do something very similar to what we did with coterminal angles. Okay, remember using k and then k as an integer with coterminal angles? Same thing here. I'm going to look at a pattern here. Oh, I forgot negative 2 pi. I've got 1 pi, 2 pi, 3 pi, 4 pi. Does it make sense that I could write all the zeros as being k times pi, as long as k is any integer? Any positive or negative whole number and 0. And again, the graph, the biggest on your unit circle, the highest things ever get for your y-coordinate is 1. The lowest they ever get is -1. And so the range is from -1 to 1. So what I'm going to show you right now is a unit circle and how the unit circle draws the graph of the sine graph. Because if you're drawing a graph, we learned from our first unit, you can always make a table of values. So you could plug in every value from your pie plate and graph it. What I'm suggesting is using your axes family. When the angle is 0, sine of 0 from my axes family is 0. When I get to pi over 2, sine of pi over 2, my y-coordinate is 1. When I get to pi, I'm back to 0. 3 pi over 2, my y-coordinate is -1. And 2 pi, my y-coordinate is back to 0. I mean, I could figure out pi over 6 and add a half. I could figure out pi over 4 and add root 2 over 2, but then that's a decimal that maybe I don't have in my head. The axes family are really easy to grab. And what I'm going to show you right now is I made this program so I have a little unit circle here. And on this unit circle, I can grab a point. So I have a point right here. And I've drawn a bunch of lines. Can you see that the blue line to the point is your y-coordinate? And the red, we're just going to look at cos and sine right now. The red line is your x-coordinate. So when I'm graphing, right, if I start and I turn on the graph for sine, let's get to 0. There I am, right at 0. It should be at 0. If I want to get that point up to pi over 2, where it's equal to 1, notice my x-coordinate is getting, my y-coordinate, sorry, is getting bigger and bigger and bigger and bigger and bigger until it hits 1. Then in quadrant 2, it's going to get my y-coordinate still going to be positive, right? We know from our cast rule in quadrant 2, sine is positive, but my y is getting smaller and smaller and smaller until it gets to 0. And then in quadrant 3, my y-coordinates will be negative. And they're going to get bigger and bigger and bigger until we get to 3 pi over 2, or 270 degrees, where it's -1. And they're still going to be negative in quadrant 4, but they're going to get smaller and smaller and smaller until you get to 1. And if we kept going around and around the circle, and I've only got it set to do measurements once around, it makes this graph. We're going to look at the cosine graph next. The cosine graph is the red. The cosine graph is your x-coordinate. So if I start graphing that, does it make sense that your cosine graph starts at 1? Because your x-coordinate's 1. And now my x, the red line, is getting shorter and shorter and shorter until it gets to pi over 2. Now in quadrant 2, my x-coordinates are negative until it gets to -1. Then that red line gets shorter until it gets back to 0. And so your sine graph and your cosine graph are almost identical. They have exactly the same shape. They just start at different points. So I'm going to go back to our notes here. I would like you to use your axes family to draw one period of your cosine graph beside the cos graph on page 515. And we'll do some highlighting with our cosine graph as well. Again, the period is 2 pi, and I would use starting at 0 is really nice for cosine, because at 0 cosine is at a maximum. How long before I hit the maximum again? It's not until 2 pi. It's really easy to see the period is 2 pi. And it makes sense that if cos repeats itself once around the circle, if sine repeats itself once around the circle, that cosine would also repeat itself once around the circle. Our domain, still everything, keeps on going forever. We're going to write a little note about the zeros. And on cosine, our zeros are at pi over 2, 3 pi over 2, 5 pi over 2, dot, 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 also negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, dot, dot, dot. And so we need to come up with a method to write all of these down. Sine was easier because it was just k pi. Okay? Cosine is not harder to recognize a pattern. I think most of you, if I asked you, do you see a pattern? What's going to be next after 5 pi over 2? 7 pi over 2. And then after that? 9 pi over 2. Recognizing the pattern is easy, but now we have to come up with a mathematical way to write that down. Okay? So, the pattern that you notice, it is an odd number times pi over 2. Agreed? Okay? Unfortunately, that's half English, half math. It's not a fully math way of writing something. So that makes sense. How do we write an odd number mathematically? Mathematically, we start off with any number, k. This is positive or negative whole numbers. If I double any number, would you agree that you will always get an even number? Taking any number, doubling it, will always give you an even number. What do we want? We want an odd number. What could I do to an even number to make it odd? We could either subtract 1 or add 1. Doesn't matter. Right? 2k plus 1 guarantees that it's odd, times by pi over 2, where k is an integer. This is method 1 for writing all of the zeros of cos. Or there is another technique we could use that's very similar to coterminal angles. If we look on our graph, we have a 0 here, a 0 here, a 0 here, and a 0 here. How much of a jump is it from one 0 to the other? Think about your pi plate. You have a 0 at pi over 2. How much of a jump is it to the next one at 3 pi over 2? Halfway around the circle, pi. And every time we add pi, we get to the next one. So similar to coterminal angles, but coterminal angles, you added 2 pi because you wanted to get right back to where you started. Here we just want to do jumps of pi. So we could say, I could start with pi over 2 and add or subtract pi as many times as I want. This would be another way to write all of the zeros of cosine. So you have a choice. What makes more sense to you? Does it make more sense to use the 2k plus 1 to think of odd numbers times pi over 2? Or does it make more sense for you to say, I'm going to start at one of them, and then I'm going to do jumps of pi to get to other ones? Question? I would say they're equal, right? I mean, This one with the brackets, notice if you actually distribute this, right, it works out perfectly to equal this. Like, but it's just different ways of thinking about it. Do you think about odd numbers times 5 or 2? Or do you think about jumps from one to the next as jumping by distances of pi? Okay? I'm going to highlight our maximum minimum. One last thing to highlight before we go is the definition of amplitude, which they have on page, at the bottom of page, or in the middle of page 515. So we talk about the distance from the center line to the middle line as the amplitude. And the middle line actually has a bunch of different names. Sometimes it's called the sinusoidal axis. Sometimes it's just called the average. Put a comma there.